again for inviting me here and for bringing the spring so nice and early. So I want to start, take everything over C. If you get bored at some point during the talk, you can try to pick some other favorite field of yours and try to figure out what works and what doesn't, but I'm going to stick with C. And I'm going to start with smooth, non-degenerate projective variety. Let me go ahead and embed it. To make this definition, sigma I, this is the usual definition of the secant variety. We take the linear spans of I plus 1 distinct points. We take the closure, and this is the ith secant variety. Those of you at my talk Wednesday heard me complain about this definition. We will give a better one today. Well, I think it's better. It's at least different. These are very useful objects, but they tend to be difficult to study because of the way they're defined. For example, while we know that the dimension of these is bounded by sort of the expected dimension and the dimension of the entire space. And we know the dimensions of the secant varieties to Veronese embedding to projective space. This was Alexander Hershowitz. We do not know dimensions of the secant varieties to, say, Segre embeddings. We know some of them, but in general, we don't really know very much. As far as arithmetic properties of secant varieties go, we know very little. And so this is what I'm studying. There are, of course, familiar cases where we know a lot. First secant variety you might encounter rational normal curve in P4, and you write down this matrix. And you learn or you figure out the ideal of x, these are the 2 by 2 minors. The ideal of the secant variety, this is just the determinant. The secant variety 2 rational normal curve in P4 is cubic hypersurface. In general, curves in P4, we have some understanding because the secant varieties are all hypersurfaces. We know the degree. You take, for example, an elliptic normal curve. Secant variety turns out to be a hypersurface of degree 5. This is a singular Calabi-Yau. This might be my favorite secant variety. It has sort of an unexpected property, which I could explain at some point, not during the talk. If you take the secant variety and you blow it up at x, you get what turns out to be a nice smooth threefold. This is a P1 cross P1 bundle over x itself, which is sort of a nice bit of geometry. I think strictly speaking it's over the dual curve. But aside from sort of small dimensional cases, we don't know a whole lot. Our help, which this was sort of going to be a surprise till it came up yesterday, comes from the moduli of rank 2 vector bundles. In particular, from my point of view, the paper of Aaron Bertram, which appeared in '92 from his thesis, is really building on work of earlier work of Laga and Narasimhan. Aaron, like was described yesterday, if you want to study rank 2 vector bundles via extensions, the space of extensions is just this. So the space of extensions is a nice projective space. This suggests that there's a, more than suggests, let me call it Pn. You should have a rational map from Pn to the moduli space, taking the representative of the extension to the bundle. And if you like, you can blow this up and make it into a morphism. This is fine, but a little ham-fisted. So,
what is P tilde? P tilde is
the resolution of the map.
I see.
Whatever, yeah. So P and tilde, if you like, and call this alpha. Take the closure of the graph of alpha. P n cross n. So we call this pi. So what Aaron did was he figured out that this pi can be factored.
So here, actually, any
Say it again?
X is any projective?
Smooth curve, smooth curve, smooth curve. Sorry, yeah, sorry. Of large degree. I don't want to be too precise because this is my motivation more than the, yeah.
Excuse me, what is M?
M was the moduli space rank 2 vector buckets. Yeah.
Large genus or large degree? Large degree or large genus?
Say it again?
You mean curve of large degree or large genus?
Degree.
Degree.
Genus at least 2. Again, this is just motivation. So we figured out that pi can be factored. As a collection of other pi's. And what are these pi's? Well, pi 0 is the blow-up of P at x. Pi 1, we need a name. We call this B1. Pi 1, we're going to go to B1. This is the blow-up of B1 along the proper transform of the secant variety. So first we blow up the curve, then we blow up the proper transform of the secant variety, then we blow up the proper transform of the second secant variety, and we keep going. This will eventually resolve this morphism.
The degree means that the degree of Rambandre or
Yes.
yeah.
Yes.
Yeah.
So we can factor this. So we've got this pi, which we pulled apart into little pieces. We blow up x, we blow up the secant variety, we blow up the second secant variety, all the way up until we resolve this map. Now this next part is sort of hidden within this paper and nearly incomprehensible the way it was written in the paper. But it's crucial for us. It might actually be incomprehensible the way it's written in the paper. But let's take a look what's happening. We have Pn. We have our x in Pn. We're going to blow up Pn along x. This is our pi 0 to B1. X. And we look at a fiber over a point x. So the fiber here over a point x is a projective space. It's not just any projective space. This is a P n minus 2, but not just any Pn minus 2. If this is P of gamma of L, this is P gamma L minus 2x. Furthermore, what happens inside here? If you look at a secant line down below, here's a point Q. This line intersects this fiber in a point. I call that point Q. As this point moves, you get a collection of secant lines. The intersections of those secant lines this fiber, trace out another copy of your curve. What we see happening is, what do I want to write down? Where do I want to put it? So if we take proper transform of the first secant variety and intersect it with fiber over a point, we get back a copy of our curve in P gamma L minus 2x. What happens when you put these all together? What is the intersection of sigma 1 with a full exceptional divisor? Well, you've got some sort of vibration over your curve. The fibers are other curves. It's curves this way and the curve this way. This actually turns out to be trivial, which is very convenient. What do you get if you intersect the second secant variety with one of these fibers? So if you intersect the second secant variety, what you're doing is you've picked 2 points, Q and P, Q apparently, Q and P. You take the plane they span, you figure out how that plane intersects this fiber. That plane will intersect this fiber in a line. Not surprisingly, it will intersect it in PQ secant line. So this is the first secant variety to this curve in still P gamma L minus 2x. The notation becomes very difficult here. Let's move up one more step. So I said we can keep going. So we blow up the curve. Then we're going to blow up the proper transform of the secant variety. Blowing up the proper transform of the secant variety in one of these fibers looks like you've blown the curve up again. And so sitting, say, over a new point y, you get another little projective space. This is a Pn minus 4. Which would be P gamma L minus 2x minus 2y. And again, you've got a copy of your curve sitting in there. If you look at sigma 2, I'm going to say this once, so I'll use really bad notation. Sigma 2, this is the second secant variety. We've blown up twice. There's a sigma 2 tilde here. There's a sigma 2 tilde tilde here. That's what I'm going to call it. Sigma 2 tilde tilde. The notation will go away in just a minute. If you intersect that with pi 0, pi 1 inverse, you get back point x. You're going to get back your curve. So now in, just write Pn minus 4. If you think geometrically what these things are, what you're doing is you're walking around your curve. And at every point of the curve, you're going to project the curve from the tangent line. That's what this is, right? This is the projection from the tangent line. So you're projecting down 2 dimensions from the tangent line, taking the image, putting it above that point on the curve, and then bundling those all up all along your curve. So you are taking all projections from the tangent lines at every point, putting them together, and stacking them on top of your curve. And then you're doing that sort of recursively in each fiber as you move down and down. This is why I erased it now. The degree has to be large enough for this to keep making sense. And in some sense it works perfectly. The moment this stops making sense, the morphism is resolved. It works out very nicely. Okay. This, well, let me say one thing on the side. So this was sort of rediscovered a couple years later by Kapranov, who was looking for descriptions of moduli space of pointed curves. So if you were going to try to build, sorry about the indexing, M0 n plus 3 bar. So this is genus 0 curves, n plus 3 marked points. How do you build a genus 0 curve with n plus 3 points? We chose n plus 3 for an obvious reason. You give me n plus 3 points in Pn, and I have a nice curve. But in Pn, you can fix n plus 2 of your points and just move the last one. And so if you take n plus 2 points in Pn, and you vary your last point, the only thing you're worried about with that last point is when that last point moves out of linear general position. In other words, it hits some sort of secant strata of these n plus 2 points. And every time you hit that secant strata, you need to blow that up to work things out. But this is exactly this, only in a much, much simpler situation. But this gives us our first lesson.
So, can I ask you one question? So, which extension class corresponds to the point on X or second value? Can you figure it out? So you blow up X inside this ambient space P. And ambient space P is the space of extension. So which extension class corresponds to the point of X?
I mean, yeah, so that I believe is worked out in Aaron's paper. Off the top of my head, I'm not gonna get it right.
Also, one confusing, if you have a same secant line, if you're moving the point, but it can be maybe same secant line, then it's still X.
Say it again?
So now you're moving the point on the X. So now you're considering the secant line. That gives the inverse image of this one. But if the secant line is same,
If the degree is high enough, you don't have.
oh, I see.
Yes, yes. Another reason to choose the degree high enough. Yes. So we rig it so that none of that happens. So here's our first lesson. What this says is that when you look at the geometry, say in Pn minus 2, or maybe down in Pn, how do I want to say it? So facts about the secant variety in Pn should somehow be very closely related to facts about the variety 2 dimensions lower. Right? Because our secant variety is giving us all of these. So somehow there should be some interplay between what's going on at the Pn minus 2 level for curves and the secant variety in Pn, and vice versa. There has to be a back and forth here. So there's lesson 1. Here comes lesson 2. So this picture, we have Pn. We have this first blow up, second blow up, third blow up. This keeps going. Michael Thaddeus in '94, in his thesis, took what Aaron had done and reinterpreted the problem as a problem about the moduli space of pairs. This is sort of a very well-known work now of sections and a rank 2 bundle. And built a collection of moduli spaces by varying linearization. Fit those spaces into this picture in such a way that what he was actually doing was sort of this first step was the same as Aaron's. You blow up the curve. Second step is the same. You blow up the proper transform of the secant variety. But then instead of blowing up over and over and over again, we contract this secant variety. We blow back down. So you get this nice collection of flips. The payoff was that these T's are much simpler spaces than the B's. And he was able to use the T's to prove nice things. But inside here, if you look at the proper transform of the first secant variety in T1, this turns out to be a P1 bundle over S2x. S2x is the symmetric product of your curve. Sigma 2 tilde, again, bad notation, but this is in T2. This is a P2 bundle. S3x. And so on. You get your sigma 3 tilde, your sigma 4 tilde. What this tells us is that, so here's sort of lesson 2. This is the way we should think of our secant varieties. We really want to think of these as projective bundles. I would like to point out something nice about this construction, just because, again, I like nice things. If you look at the difference between what Aaron was doing and what Michael was doing, if you take, say, a 3 secant 2 plane, here, you blow it up. I didn't draw that picture right, but that's okay. You blow it up. You blow up the points. In Aaron's picture, nothing happens after that. It just stays there. But in Michael's, so at this stage, nothing happens. No change. Same wrong picture. But what happens from here to here, the way this flip works, so we told you that sigma 1 tilde in T1, this was a P1 bundle. Secant variety here is a P1 bundle over S2. To go from here to here, you simply blow it up. So now that exceptional divisor is a P1 cross PR bundle over S2. And here, we just shrink the P1s. So we're left with the PR bundle over S2. So it works very simply. But what that means is that when you go from here to here,